السلام عليكم ورحمة الله وبركاته. أسعد الله صباحكم جميعا. اليوم إن شاء الله مكملين معاكم بشابتر 8، والمرة الماضية توقفنا عند هذا السلايد وحكينا بهذا الشابتر عن internal convection. Internal means fluid flowing inside circular or non-circular pipe or duct. So the flow is bounded from all direction, and we are tackling the issues related to heat transfer, or to be specific, convection heat transfer. So as a continuation of the average velocity, one of the objectives was calculating the average velocity and average temperature. So let's start with the average velocity. Okay. So the value of the average velocity, as we agreed last time, remain constant along a pipe, but there is a condition. That condition was constant pipe diameter and, anyone remember? Constant density. Okay, so we have two conditions in order to say that the average velocity remain constant along pipe. Okay, constant pipe diameter and constant density. So the value of, but how we determine this value? Now we'll see the equation, the derivation of this equation. The value of the average velocity at some streamwise cross-section is determined from the requirement that the conservation of mass principle be satisfied. So in order to derive the equation for V averaged, we need to start from conservation of mass equation. Remember, I think some of you will take this equation in fluid mechanics. So here is the equation. Okay, m dot mass flow rate equal density multiplied by V average multiplied by cross-sectional area, or m dot equal, from definition, integration over control area over the cross-sectional area, and inside this integration we have rho multiplied by velocity profile multiplied by area. So this is derivative of this term. Okay. So as you know that at each instant this profile has an equation. Okay, and this equation we name it u as a function of r. Okay, so this is not multiplication here. This means u as a function of r. This is a function. So u equal certain function a, for example, multiplied by r plus b, etc. Okay, it could be parabolic, it could be linear. So here we have parabolic, so we expect something like this. So the caption, before continue in this derivation, let me read the caption for you. So this caption, figure 8.2, average velocity is defined as the average speed through cross-section for fully developed laminar. Okay, so this derivation special for fully developed laminar. Okay, again it's valid for turbulent, but we need the velocity profile. If it is available, it's good. Okay, we can substitute directly. Okay, why fully developed region? Because the profile become constant, as I'll explain later on. So this profile, velocity profile, vary from one location, from this location to another location to another location. Okay, so but it become constant when we are in the fully developed region. Okay, I'll talk about this region later on. Okay, so let me erase. So yes, so m dot equal rho V average cross-sectional area, which is equal to integration over the cross-sectional area. Now, in order to find V average, I'll divide this equation rho by cross-sectional area for the both sides of this equation. Cross-sectional area. As I told you at the beginning, once the density remains constant, does not change, it will go outside the integration, and I can cancel it out with rho. Okay, So this is equal, and instead of area cross-sectional, I can substitute if this pipe diameter or radius is r. Okay, I can substitute instead of cross-sectional area by r squared. Okay, so this equation can be written as 1 over by r, or r capital squared, from 0 to r. Okay, u as a function of r multiplied by the area. So if the area equal by r squared, the cross-sectional area will equal to, so the derivation of this one, so I can write it instead of r as a constant, I can write it as a variable, r small. Okay, so this is 2 by r dr. So here instead of the cross-sectional area, I can write it as 2 by r dr. Okay, so by will cancel out with by, so we end up with 2 over r squared. Okay, integration from 0 to r, u as a function of r multiplied by r dr. Okay, so this is equal V average. This is the value of V average. Okay, so for any point on the pipe, whether we are in the fully developed or whether we are at the entrance of the pipe. Okay, so but if we are in the fully developed laminar region, then the V average is half the maximum velocity. This is a rule. So V average is equal to uh, sorry, V average equal V max divided by 2. Okay, so this is a rule for which scenario? For fully developed laminar pipe flow. So this is the general equation for any scenario. Okay, let me erase this and keep the other steps. So here m dot is the mass flow rate, the rho is the density, AC is the cross-sectional area, and UR is the velocity profile. So you can read it. So let me erase also this one, because UR is very important. Some of you think that this is U velocity multiplied by R. This is not correct. This is U as a function of R. This is function. That means U is variable and it depends on R. Then the average velocity of for incompressible, why we call it incompressible? To keep this assumption, density equal to constant value. In a circular pipe of radius r, this is to make sure that the pipe diameter is constant, d is constant, or instead of d, we can write r is constant. So here is the two condition. So if I rearrange and walk through the derivation, we'll end up with this equation, which is the same as what we did a few minutes ago. Okay. Okay. So you must remember this equation. Not all of it. You must know that V average is equal to 2 over r squared integration u as a function of r multiplied by dr. How about averaged temperature? Okay. We agree that average velocity remains constant, but how about the temperature? In fluid flow, it's convenient to work with average or mean temperature. Instead of subscribed average, we write mean, okay? Which remains constant at a cross section, okay? So if we have a pipe, so at the entrance, we have T mean for the entrance, okay? For the exit, for example, we have T mean exit, okay? For this location, we have T mean at certain X, okay? So this is T mean at the exit. I can write it T mean at L. Here T mean at X equal to 0, okay? Here at any X. So which remain constant at a cross section, okay? Only at certain location. This is the meaning of this word, of the sentence. So T mean remain constant at a cross section, not along the pipe, okay? Velocity, the average velocity remain constant. I think I mentioned this information in the previous slide. I'm not sure where I mentioned it, okay, but it remains constant. Velocity, the average, remain constant along the pipe. And remember that we mentioned that we need to, so yeah, here it is. In the flow, the average, which remain constant in incompressible flow with when the cross-sectional area pipe is constant. So we are talking here about the whole pipe length, okay? So we are talking about the whole length, okay? But for the temperature, we are talking about certain location, okay? So here T mean across this location, across this cross section remain constant. T mean at this location uh, remain constant. T mean at this location at cross section become constant. Unlike the mean velocity, the mean temperature change in the flow direction. Okay, so T mean at this location inlet is not the same as this location X, and it's not the same as this location exit or L. So this is vice versa the mean velocity. Mean velocity remain constant in the flow direction. Why T mean keep varying? Because this is a special scenario if we have heat or cooling. Okay, if we have heating or cooling, then T mean will become vary. And this is the case here in this course because we are dealing with heat transfer, convection. So we have a Q entering the cross section. Okay, we have a Q entering. So if the Q entering, then we expect that the T averaged or T for any layer will vary. Okay. The value of the mean temperature is determined from the requirement that conservation of energy principle are satisfied. Okay, is satisfied. So for determining or for deriving the equation for V averaged, we benefit from conservation of mass equation. Now for determining T mean, we'll benefit from conservation of energy equation. Third equation in fluid mechanics, if you remember, for who took this course. Okay, so E dot fluid energy for a fluid is equal to M dot CB T mean. Okay, and I think you are familiar with this equation for all of you. I'm talking about all of you because if you remember, we are talking about rigid body or if we are talking about open system, this energy could be delta U. Then we are talking about m dot CV delta T. Okay. And if we are talking about system that has inlet mass, outlet mass, then E dot will equal H, and this is equal M dot CB delta T. So here, I think you guessed that this energy, we mean that we are calculating the enthalpy, okay, which is equal to M dot CB delta T, or T mean. Okay, so this is the general equation, but this energy is equal to integration over for the m dot, okay, with respect to m dot, CB, okay, CB, T as a function of R. This is the temperature profile. This is variable. And it represents the temperature profile. Okay, temperature profile. Okay. And this value represents constant value. This integration with respect to dm, or instead of dm I can write rho multiplied by velocity multiplied by cross-sectional area. So this is could be written as rho. Instead of velocity I write velocity profile equation multiplied by d cross-sectional area. And instead of d cross-sectional area I can write 2 by r dr. And now this integration, instead of take it across cross-sectional area, we can take it across 0 to r. Okay. Okay. So CB, as we agreed, and rho constant. So we'll take it outside the integration. And here in the other side, so this equation equal this one. So I'll divide both equation with m dot CB here, m dot CB. So this m dot CB will cancel out. And instead of writing m dot, what I can write? Can write rho V averaged, okay, multiplied by cross-sectional area, which is by r squared. Now CB cancel out with CB, okay. The cross-sectional area, this is equal to 2 by r dr. So by with by cancel out, and we end up with, so here is the denominator. We have rho, we have the average, okay, we have pi r squared, and we have CB. Here in the denominator or numerator, we have, this is CB, temperature profile, okay, density UR 2 by R dr. So CB cancel out, as I mentioned, with CB, rho cancel out with rho, pi cancel out with pi, and we end up with, so T remain inside the integration UR and R dr. So this is temperature profile, velocity profile R dr divided by R squared, here it is, and V average, and we'll take 2 outside the derivation, okay, 2R. So this equation, we'll use it to find the mean temperature at any location, okay, at any location. So then the mean temperature of a fluid with a constant density, this is why we take it outside the integration, and constant specific heat, okay, we'll take it again outside the integration, in a circular pipe, constant diameter can be expressed as this equation. Okay, so هذه المعادلة المفروض منكم تحفظوها. Okay. So these two pictures represent the ideal and actual scenario, and this is what usually happens. T average is at this. This is T mean. Okay, so T surface usually very high, and the T minimum become very low. So if you can notice, this is the temperature profile, and it is opposite to the direction of velocity profile. Okay. طيب. Laminar and turbulent flow in tubes. Flow in a tube can be laminar or turbulent, depending on the flow condition. Which flow condition? One important parameter is the velocity of the flow. Okay. In addition to other parameters like diameter, type of fluid, temperature, okay, etc. The fluid flow is streamlined and thus laminar at low velocities. See here, this is the most important parameter, the velocity. Okay, so if we have very low velocity, then we are talking about laminar scenario. But turns turbulent as the velocity is increased beyond the critical value. Of course, why we are focusing on velocity? Because we are dealing with incompressible and constant pipe diameter. So Reynolds number, which is the most important dimensionless number that describe laminar or turbulent flow we have, it's equal to V rho V d over mu. So if we are talking about constant pipe diameter, so this variable constant will not affect. If we are talking about incompressible, then these two values as constant, and we end up with this value. Okay, so this is the most important value that will affect the Reynolds number value. Transition from laminar to turbulent flow does not occur suddenly. Rather, it occurs over some range of velocity, where the flow fluctuates between laminar and turbulent flows before it becomes fully turbulent. زي ما ذكرنا في الاكسترنال flow. بالاكسترنال flow حكينا إنه الفلو بيعدي 3 regions. Okay, بيكون laminar بعديها بيروح transition بعديها بيروح turbulent. Okay, so بيكون laminar بعديها بيروح على transition بعديها become fully turbulent. Okay, so على مراحل. Here نفس الشيء the same. Okay, so it is fluctuates. أحيانا بتكون laminar أحيانا بتكون turbulent. Laminar turbulent هذه المنطقة بنسميها transition. Okay, until it become fully turbulent. Most pipe flows encountered in practice are turbulent. So industrial application دائما الفلو بيكون داخل البايبس تكون ايش turbulent أغلب الأحيان. Laminar flow is encountered when highly viscous fluids such as oil flow in small diameter tubes or narrow passages. عادة لما نتعامل مع very viscous fluid رايحين نتوقع إنه الفلو بيكون إيش؟ laminar. هدول في الابليكيشنز اللي بيكون عندي فيها الفلو very viscous like الكرود oil زيت الخام. زيت الخام بيكون very viscous. Okay, so we expect that the flow is laminar, and especially when we are dealing with very small diameter. Transition from laminar to turbulent flow depends on Reynolds number value as well as the degree of disturbance of the flow by surface roughness, by vibration, and fluctuation in the flow. Okay, so صح احنا حكينا Reynolds number depends on certain values like density, velocity, pipe diameter, viscosity. So it's mentioned here. One of the most important parameter is Reynolds number and its parameter, which is density, velocity, diameter, mu. Whenever we mention Reynolds number, we mean that we are dealing with this parameter also. So this is one important parameter, as well as degree of disturbance of the flow. So this is another very important parameter, degree of disturbance. ايش هم الديستربنسز اللي ممكن تأثر على الفلو؟ like surface roughness. So زي ما حكينا الرينولد نمبر فيه له parameter 4 parameters for example or 3. كمان degree of disturbances إلها parameter like surface roughness، خشونة السطح هل هو smooth ولا rough surface. Pipe vibration if we have external source of vibration. okay. إجا حدا مثلا وهز الأنابيب بتحول الفلو من streamline ل non-streamline تصير transition or become turbulent. okay. And fluctuation in the flow. طبعا ال fluctuation of the flow مش شرط يكون سببه السرعة، سرعة مثلا الووتر for example مثلا بنتعامل مع الووتر، قد يكون other parameter. ممكن يكون عندي two phase في البايب. okay. ممكن يكون عندي gas flow بالتالي بيعمل fluctuation بسرعة الووتر. okay. طيب the flow in a tube is laminar when Reynolds number less than 2300. okay. But become fully turbulent when Reynolds number greater than 10,000. okay. But usually we are not going to deal with this range. okay. So this range is acceptable for laminar, but for turbulent we'll go lower than this value. okay. And the transition in between, I'll tell you what is the range of Reynolds number for internal flow. okay. So this range is special for this chapter. In the previous chapter external we have another range for Reynolds, but for internal this range will adapt this one but will not adapt this one. okay. I'll tell you in a while which is the ranges. طيب mainly we'll concentrate in the tubes, flow in the tubes, but what if we have non-circular? okay. For a flow in a circular tube, the Reynolds number is defined as Reynolds equal V averaged multiplied by diameter divided by kinetic viscosity, or we can use the density over absolute viscosity. okay, multiplied by V average multiplied by diameter. Now instead of V average, I can benefit from the equation which says m dot equal rho V average multiplied by cross sectional area. Or instead of writing V average, I will write m dot multiplied by rho multiplied by or divided by rho divided by cross sectional area, this one. So here we have rho, so this rho will cancel out with this rho. okay. Here we have diameter, it will cancel out, and here we have 4, it will become up here, so here we will have 4. So this is the final format, 4 multiplied by m dot divided by mu by d. So in solving problems, either we'll choose to calculate Reynolds number from here or from this equation or from this one. So it's up to you. So it depends on the parameter of the problem. okay. So sometimes the problem will come and give you everything except density, so you must use this one. okay. And sometimes it gives you everything except density and viscosity, and you will have kinematic viscosity, so you'll use this one. okay. Or sometimes V is missing and everything is given, so you will use this one. okay. So it depends on the given information in the problem. So this is for circular tube. Now for a flow through non-circular, we need to calculate what we call it hydraulic diameter. So hydraulic diameter for non-circular tubes is calculated from this equation. So d hydraulic equal 4 multiplied by cross-sectional area divided by parameter, or weighted parameter to be specific. okay. So 4 multiplied by cross-sectional area divided by weighted parameter. Weighted parameter means الجدران أو المحيط المبلل. اللي الفلو بيغمره. اوكي، يعني مثلا هون كل الاجزاء زي ما انتم شايفينها colored with blue. اوكي، على سبيل المثال اذا كان عندنا الفلو water. so المحيط هون مبلل بالكامل. here the same، كل الجدران لونها ازرق، بالتالي عندي الفلو مغطي بالكامل. here the same. here in this scenario this portion. اوكي، وكمان عندي من هذه الجهة this portion is not uh, is not filled with water, or it's not wetted with the water, so will not include it in the calculation because will deal with the wetted parameter only. Okay, and here is example for how to calculate each parameter. Okay, this is the cross-sectional area, and here is the wetted parameter. Okay, here the same for rectangular duct, here for square duct. Okay, so whenever we are dealing with non-circular tubes, that means we'll have duct. So this duct will be in square or rectangular, or it could be channel. Under most practical conditions, the flow in a tube is laminar for Reynolds number less than 2300 and fully turbulent for Reynolds number greater than 10,000. And as I mentioned, will not use this range. Okay, instead, but it should keep in mind that in many cases the flow becomes fully turbulent for this range. Okay, so above 4000 or 4000 Reynolds number, then this is fully turbulent. Below 2300, this is laminar. Between them, this is what? Transition. Another objective of this chapter is to learn how to calculate the entrance region and to define it. So at the beginning, we'll define it, then we'll learn how to calculate this region. Here we have a flow. This is the entrance. Okay, and here is the exit, or this pipe will continue for infinity. Please notice that the pipe diameter here is constant. Okay. Another thing you must notice that we have two regions, as we mentioned in the objective. We'll learn how many regions we'll have. So we'll start with the velocity. So we are talking here only about velocity profile developing. Where is the velocity profile? In this picture, here it is. So here at the beginning, at the entrance, the velocity almost, this is the velocity profile, which is constant. V here is constant, which is equal to V infinity. Okay. Now, we'll not call it V infinity, we'll call it V entrance. Now, after a certain location, this location, for example, so here at location x equal to 0. After certain location, x1, the profile start developing. Okay, start developing. After another location, we have further developing. Okay. After third or fourth location, we have another developing. Okay. Then the velocity profile become fully developed. Okay. This is fourth location. One thing is very important to notice that yes, we have constant pipe diameter, so and we have incompressible flow, of course. Okay. Then V average for the whole pipe length is constant. Okay, it will not change. Its value will not change. Now, how about the regions? The region where the profile developing from one location to another until here. Here is the moment where the profile become developed. So if I'll take another location, this shape will repeat it over and over. Okay, it will repeat it over and over. It will not change. So at the moment that the fully developed profile appear, okay, we call this region from the entrance. This is the entrance. Here is the entrance. Up to this point, we call it hydrodynamic entrance region. Okay. Now here, from the point of the profile become fully developed till infinity. Okay, if there is no any disturbances, we call this region dynamically fully developed region. Okay, so this is fully developed region, hydrodynamically fully developed region, and this is the entrance region. So we have actually two regions, entrance region and fully developed region. Or we call it, instead of entrance dynamic entrance region, we call it developing region. Developing, where the profile keep developing. Okay. Here, this region, fully developed region. I can write it in this abbreviation. Fully developed region. So it becomes fully developed. It will not develop furthermore. Okay. Okay. Let's define each region alone. So velocity boundary layer. The region of the flow in which the effect of viscous shear force caused by fluid viscosity are felt. So this is why here the velocity near the walls 0. Why? Because of no slip condition, because of friction, because of viscous. We call this region as velocity boundary layer. Where is this region? Here is the region. Okay, here. This one. The hypothetical boundary surface divides the flow in pipe into two regions. So because of the boundary layer, we'll have two divisions of the flow, or two regions. Boundary layer region, which colored in the green color. So this is the viscous effect and velocity change are significant. So here you can notice that we have, this is here 0, okay, here is greater, here much greater, but then it become constant. Okay, so number of layers uh, uh, at x equal to 2, for example, number of layers affected from the viscous become larger, then it suddenly become constant. Okay, here we have this point constant. Okay, so the same as we talked in the previous chapter when we have flat plate and flow. Okay, we mentioned that at each location the effect from viscous ends at this location at this point. Here furthermore, here furthermore. Okay, so if we connect them with a layer, then we call this region as boundary region. Okay. So this is the boundary layer region, and it's colored in the green color, as you can see. So it become united at this x. Okay, at this axis, it become one region. Okay, when it's entered the fully developed region. Beyond this region, still developing, and they are separated. See it again. They are separated until they reach fully developed region. The other region is irrotational core flow region. Irrotational. Where is it? Here it is. This is the irrotational core flow region. Okay, here at the middle. So this region is irrotational, which is colored in the blue color. Here it is, irrotational flow region. So the frictional effects are negligible. We are far away from the pipe surface, and the velocity remain essentially constant in the radial direction. So if I come and ask you define the rotational flow region, you must say that the friction effects are negligible and the velocity remain constant in the radial direction. So here we are dealing with the radius. So it remains constant, the velocity. Okay, so they are constant. And this region vanish once we enter the fully developed region. Hydrodynamic entrance region. Hydrodynamic entrance region. If I come and ask you define it, this is the region from the pipe inlet from the entrance, okay, to a point at which velocity profile is fully developed. When the velocity profile developed at this point, then this region as a whole, we call it what? Hydrodynamic entrance region. Okay. Then this region has a length, and we call it hydrodynamic entry length, LH. This is the length of this region. Which region? This region. Okay, this length. This length, this region, we have LH, L hydrodynamic. LH means we are dealing with the velocity. We are dealing with the hydrodynamic. We have another length for thermal entry region when we'll talk about temperature. So this slide special for velocity as I mentioned. Okay. Another definition, hydrodynamically fully developed region. The region beyond the entrance region, which starts from here, okay, beyond the entrance region, in which the velocity profile is fully developed and remain unchanged. As I mentioned, the velocity profile repeat itself. Okay, it will never change. And take a very focus. Please focus on this profile where we have the maximum velocity exactly at the center line. Okay, so only this layer at the center line, its velocity is maximum. Then the velocity for the layer adjacent is lower. Okay, so please concentrate on this point. Flow in the entrance region is called hydrodynamically developing flow since this region where the velocity profile keep developing. Okay, ممكن نسميها developing flow region. Okay, is called hydrodynamically developing flow. Instead of hydrodynamic entrance region, we have another name for it. Okay, which we call it developing flow region. Now, this slide special for temperature profile and temperature pipe divisions. Okay, again we have same regions. Okay, this is thermal entrance region or thermal developing region. This is thermally fully developed region. Okay, and we have same effect. We have thermal boundary layer and we have core boundary region or core region. Fluid properties in internal flow, this chapter talks about internal, are usually evaluated at bulk mean fluid temperature. Remember in the external flow, we evaluate the property of the flow flowing on top of flat plate based on T film, which is the average temperature between T surface and plus T infinity over 2. This is how we evaluate the property in the external. Now in the internal, we have something similar, but we call it bulk mean fluid temperature. Okay, and we'll give it symbol T bulk, which is the arithmetic average mean temperature of the inlet and the exit. So T bulk is equal to T mean inlet plus T mean exit divided by 2. So here, as I mentioned, we have T mean at the inlet, and if we have here the exit, we have T mean for the exit. So if I add them, arithmetic averaging, so it will give us T bulk, and we'll go and find the other properties like density, conductivity, viscosity, Prandtl number, etc. The thermal entrance region we can define as the region of a flow over which thermal boundary layer develops and reach the tube center. Okay, so as you can see, here we have a thermal boundary layer, and here we have another thermal boundary layer from this side. Once they met together, then we'll end from the entrance region and we'll start the fully developed region. For this region, we have thermal entry length, L thermal, and it represents the length of this region. The thermally developing flow, the flow in thermal entrance region, this region where the temperature profile develops. Okay, so either we call it thermal entrance region, or we call it thermal developing flow. Thermally fully developed flow, okay, which is this region where the profile will not change anymore. The region beyond the thermal entrance region where the two boundary layers met together, in which the dimensionless temperature profile remain constant. Dimensionless temperature profile. Remember this dimensionless when we took T minus T surface over T surface minus or T infinity minus T surface. We took it earlier when we derived equations. Okay. Now, if we said define fully developed flow without specifying whether it's hydrodynamically or thermal, then we must answer it, or we must define it as the region in which the flow is both hydrodynamically and thermally developed. Okay, so velocity profile become constant, and here temperature profile become constant. The entrance region. Now we took two lengths, hydrodynamic entrance length and thermal entrance length. Which one is larger, LH or L thermal? In order to answer this question, we need to ask ourselves whether we are in the laminar region or whether we have laminar flow or we have turbulent. Okay, because this question is very essential. Okay, if we are talking about laminar flow, then we can answer which one is the greater, LH or L thermal. That means we have a relation for both of them. But before tackling this issue, let us take a look to these two profiles here in this picture. Okay, so as you can see, this is the velocity profile, okay, in red color, and the one in blue color represents the thermal boundary layer. So yes, excuse me, I call this velocity profile. This is velocity boundary layer, and here we have thermal boundary layer. So this figure expresses the or demonstrate the variation of the friction factor and convection heat transfer coefficient in a flow direction for a flow in a tube where Prandtl number greater than 1. Okay. So as you can see here, if we are talking about first of all the velocity boundary layer, okay, velocity boundary layer, the effect of entrance region vanish here. Then I'll take a line like this, okay, and I would say that the friction effect vanish here and it become constant. So what do we have here? We have a diagram x, the length or the location at the pipe and on the x-axis, and on the y-axis we have the convection coefficient and the friction coefficient. Friction coefficient affecting what? Affecting velocity. And H affecting or affected by temperature. So we will relate friction with the velocity boundary layer. So the friction coefficient, and notice that it is local because we'll take the entrance, the region where the entrance ended, okay, in consideration. So at the beginning of the entrance, we start with very high value of the friction because the friction are felt strongly on the entrance. Then this friction, as long as we are going deeply inside, the boundary layer start vanishing until this point. So its value become decreasing until we reach this point, and in the fully developed region, it becomes constant. Okay. Same thing happens to the H. Here is the thermal boundary layer, and we'll relate H with the thermal boundary layer. So here is the thermal boundary layer. Once it is vanished, then the fully developed region starts, okay, or thermally developed region. So you can tell easily that the H at the entrance very huge, then it decreases, and when it reaches the thermal fully developed region, it becomes constant. Okay. So once both profile become constant, where we are talking about this at this location onward, then we call this region what? Fully developed region. We mean hydrodynamically and thermally. Okay. Now let's take a look to the equation. As I mentioned in the previous slide, that if we are talking about hydrodynamically fully developed region, then whenever we are in this region, fully developed region, that's mean u as a function. U, but by the way, if we have a pipe, then this u as a function, this is velocity profile from the entrance, it keep change, correct? This is what we mentioned earlier. Okay, it keep it change until it reach the fully developed region. So u, which is the function or the velocity, it depends mainly on two parameters, x and r, where x is the length of the pipe, arbitrary locations. Okay, so this is represent the location along the pipe, and r represent the radius of the pipe. Now, if we are in this region, then u is depend very strongly on both parameters x and r. But once we are in this region, fully developed region, I mentioned that the velocity profile keep unchanged. So u does not depend on x, but it depends mainly on r. So it does not depend on x, it depends on r. Why? Because velocity magnitude vary along the radius. But in terms of x, if this is x1, this is x2, I said that the profile repeats itself, same magnitude. Okay, so it will not anymore factor of x. It depends only on r. This is why if we take the partial derivatives of the velocity profile with respect to x, we can say this is equal to 0. Why it's equal to 0? Because velocity profile, which is at the beginning function of r and x in the fully developed region is not anymore function of x. It's only function of r. Okay, this is especially when we are in the fully developed region, but this is not correct if we are in the entrance region or in the developing region. Same thing for the thermally fully developed region. Okay, thermally fully developed region, once we enter the fully developed region, then the temperature, which is function of r and x, in the fully developed region, it's not anymore function of x, so it's equal to 0. By the way, this is the dimensionless temperature equation. From here, we can tell easily that the surface heat flux entering the pipe, we have here a pipe and we have q dot x entering, or q dot surface, is equal to h local multiplied by ts minus t mean. Okay, and this is equal to conduction equation, which is equal to k multiplied by delta t over delta r, where r is equal to r capital. Okay, at the surface, we are talking about at the surface, where we have, so if we have here q from inside to outside or from outside to inside, then we are talking about this region between conduction and convection. Okay, or we can say hx equal to k multiplied by delta t or divided by ts minus t mean. What you can tell about this equation? Oops. What you can tell about this equation? Okay, this slide totally talks about the fully developed region. Now, if we take the surface as I mentioned, and we try to write an equation that describes the variation of Hx, we'll see that it's a function of thermal conductivity, which is constant. T surface minus T mean remain constant in the fully developed region. Okay, this function, if we derive it with respect to r, remain constant. Why? Because T in the fully developed region depends on the radius, not on the location x. Okay, so as a whole, this whole equation is constant. As a conclusion, h is equal to constant value, and this is the same conclusion that we got from here. H start to be constant after we entering the thermal fully developed region. Okay, so in thermally fully developed region of a tube, the local convection coefficient is constant, does not vary with the location, with the x. Therefore, both friction, which is related to wall shear stress, and friction and convection remain constant in fully developed region of the tube. So we have a good relation between friction and delta B pressure drop, and we have good relation between H and Q, heat transfer rate. So the pressure drop and heat flux are higher in the entrance, true or false? True, because friction coefficient is higher and H is higher in the entrance. Here, this is where x equal to 0, this is the entrance. And the effect of the entrance region is always to increase the average friction factor and heat transfer coefficient of the entire tube. So if we have, for example, at the entrance, very high value, okay, so this H will start from even higher value, then it will become constant. So the effect of entrance region is always to increase the average value. So instead of having this average value, H average here, So if you have very strong effect from the entrance region, this average value become even higher. Okay, this is the meaning of this sentence. And the effect of the entrance region is always to increase the average friction and edge. Okay, for both. But which value? The average one. Okay, when it become constant. So instead of having constant value at this magnitude, if we have a stronger effect from the entrance, those magnitudes will be shifted upward to have higher values for both. Now, what about the laminar and turbulent? How they will affect those values? In laminar flow, the hydrodynamic and thermal entry length are given approximately as L hydraulic. Hydraulic means for the velocity profile entrance region. So this is the length of this region. Okay, hydrodynamic entrance region for the velocity. It's equal almost approximate because this is correlation. 0.05 multiplied by Reynolds number multiplied by diameter. So the hydrodynamic entry length depends on Reynolds and depends on the diameter. How about thermal for the laminar? So this is entry length for thermal for the temperature for the laminar scenario, and it's approximated equal to Reynolds, Prandtl, diameter, 3 parameter. So which one is bigger, LH or LT? What do you think? So if LT, L thermal is equal to Prandtl multiplied by LH, which one is higher? For the turbulent flow, LH hydrodynamic entrance length and LT turbulent thermally entrance region is equal to 10 multiplied by diameter, 10 diameter. And it's mainly function of diameter only, not on the Reynolds number. The Nusselt number and H values are much higher in the entrance region. So here in this diagram, we have here x divided by t dimensionless, location divided by diameter, and here we have Nusselt number for H hydrodynamic and Nusselt number for thermal. And you can notice easily طبعا بالاعتماد على رينولدز نمبر في حالة اللامينر. هذا الكيس اللي عندي هون only for laminar. Okay, sorry, this is we are talking about 10 to the power 4. This is turbulent. Okay, so هذه this scenario for turbulent flow. Okay, for turbulent flow. So the Nusselt number for both of them, hydrodynamic or turbulent, almost the same. You can notice clearly. And they are identical, become exactly the same for fully developed region. Okay, so this is entrance region, and here we have fully developed region. And another notation that it starts from higher value. This is the entrance, and it become constant in the entrance in the fully developed region. So here is explanation for this figure. Nusselt number reach a constant value at a distance less than 10 diameter. Here is 10 diameter, and it become constant at this Reynolds number. Okay, and thus the flow can be assumed to be fully developed for x greater than 10 diameter. So مثلا لو كان عندنا experiment وجا حد حكى لك وحكى لك انه هذا الفلو turbulent، حكى لك حدد لي منطقة الفولي ديفلوبد، سمبلي بتروح بتجيب متر وبتضرب 10 multiplied by diameter وبتقيسها distance، تحكي له at this location onward we have fully developed region simply. Okay, لأنه هي القانون بيحكي لك 10 multiplied by diameter turbulent flow fully developed region starts. لأنه هذا الطول يمثل طول الهيدروديناميك والثيرمال turbulent entrance region. Okay, very simple. The Nusselt numbers for uniform surface temperature and uniform surface heat flux condition are identical. Here you can see in this legend that this Nusselt number for thermal, it's measured at constant surface temperature, but the hydrodynamic Nusselt number measured at constant heat flux. And both of them, this is dashed line, constant heat flux, and this blue continuous line is constant temperature. Both of them identical beyond the entrance region. Are identical in fully developed region and nearly identical in the entrance region. There is no big difference actually between them. Okay, they are very close to each other. So this is how we calculate the LH, and this is how we calculate LT. Which one is bigger? It depends on the value of the Prandtl number. Okay, depends on the value of the Prandtl number. In turbulent flow, the hydrodynamic and thermal interlink, hydrodynamic LH, and this is LT, are of about the same size and independent of the Prandtl number. Okay, so here is the equation. LT turbulent, LH turbulent equal to 10D. So they are equal and they are independent on the Prandtl number. Okay, here is the equation. The entry length is much shorter in turbulent flow. Shorter than whom? Than the LH laminar and LH LT thermal laminar. Okay, so it is much shorter, and it depends on the Reynolds number is weaker. Okay, so this is a fact. Why? You can compare even the equation. This is 10D and LH laminar. The equation was 0.05 Reynolds number diameter. Okay, so this is 0.5 Reynolds number multiplied by diameter. Here 0.05 Reynolds number diameter Prandtl. So if you compare these two values, you will find out that this is very shorter, okay, very less than the laminar scenario. Okay, so I'll stop up to this point. Okay, next lecture I'll start with you this issue. Okay, until then, stay safe and see you soon.